Okay. So yeah, thank you for the introduction. And then so today I will talk about my thesis that I have been working for the past 6 years. And the title of the thesis is the search for extreme BCG cluster at 0.2 to 1.3 redshift. And this project, the goal is to study galaxy cluster and agent feedback. And I try my best to try to explain what that means as we go along. Okay, they always say that the first slide is the most important slide. So, okay, so here is my most important one. As everyone have been using Zoom for a while now, I will do something interactive. So the question is, which one of these galaxy cluster you think is unique? You are feel free to answer what you think is the most unique galaxy cluster. So each one of these is a galaxy cluster. And then, so my project is trying to find what are the unique galaxy cluster, and then what do you think is a unique one from this picture? Okay, wow. So a lot of people, okay, we have 70% of people already responding. I'll give you 5 more seconds. 3, 2, 1. Okay, so here is the result. Everyone thinks it's number 3, which is which is exactly what I'm trying to find. I want to talk about this for this talk. So, okay, let's go back to the talk. Okay, so the reason that number 3 or the Phoenix cluster is the most unique one of all these 6 is because of the central galaxies or the BCG or brightest cluster galaxy, which in the middle of the galaxy cluster have a color blue with this filamentary like structure, which are very different from any other known cluster that we know of. And that's what makes the Phoenix cluster really unique compared to all these other galaxy clusters. Okay, before I talk about galaxy cluster, let me actually start about what a galaxy is first. So a galaxy, when you think about galaxy, you always imagine like this giant tab on the sky that have a lot of stars next to each other. But if you actually zoom out, you can see that a galaxy are actually not just one side, it's actually symmetric, and then it have the whole thing is called a galaxy. But if you go way out of the Earth and go out of the solar system and the galaxy itself, you can see that the galaxy actually have this spiral shape. And then these are examples for the Andromeda galaxy. And then there are another kind of galaxy called elliptical galaxy, which are more elliptical-like shape and then with no spiral structure that you can see now. But these are the most massive galaxy that we know of, usually in the elliptical shape instead of the spiral phase like the Andromeda galaxy. Okay, so in the outline of this talk, I will talk about what a galaxy cluster is, what do we know about it, and then we talk about the CHIPS survey, which is what Mike just described for the in the introduction. I talk about the evolution of agent activity, and then I just do a very quick conclusion. Okay, so what are galaxy cluster? Galaxy cluster are a cluster of galaxy or a group of galaxy that are coming together, but the main property is that it actually confined in a gravitational field, so it's actually a bounded object, so it doesn't move around and it's actually orbit around each other. And this one is example of a galaxy cluster Abel 370. You can see that these red dot here are individual galaxy, and combine of them call them a galaxy cluster. So this cluster have this one as a brightest cluster galaxy or the BCG, and then you can see this beautiful gravitational wave arc, which some people use to study galaxy cluster as well. Okay, so what are the property of the galaxy cluster? It's the most massively bounded object in the universe. It consists of a lot of galaxy members. So like in each one of these are members of galaxies, and then the whole thing is a galaxy cluster. It holds a central BCG in the center and have a giant dark matter halo. It usually contains an extremely hot gas inside the halo itself. So this blue emission here are emitted the X-ray emission from the, and then that coming from and that's what we actually use to study the galaxy cluster. Okay, so there are many major events that have imprinted in the X-ray morphology. So that means the shape of the X-ray emission can tell you a lot about what's happening inside the galaxy cluster. For example, you can see the ongoing merger. So here are the bullet-like shape. in the galaxy cluster. So that means the galaxy cluster are colliding, and at this collide, it creates this bullet-like shape. Or you can also see sloshing from X-ray, so that as the galaxy cluster are moving, then the gas itself inside the cluster have been moving around, and then that also what's called sloshing. You can also see bubble or cavity inside a galaxy cluster X-ray. So these are the cavity that you can be detected using the X-ray emission. Okay, so where is the X-ray photon come from? The X-ray photon come from the mechanism called thermal Bremsstrahlung. So that what happened is, at the high energy electron coming from the hot gas moving past the ion, then it gets deflected and changing its direction. And at the change direction, it emits this radiation in the form of thermal Bremsstrahlung in the X-ray. The radiation is actually strongly dependent on the density. So here you can see that it actually depends square to the density and only 1/2 to the temperature. That means as a galaxy cluster, the center part is the most dense part of the galaxy cluster. That means there will be a lot more X-ray emission coming from the center compared to the outskirts. And what that implies is that the center of the galaxy cluster would have been cooled so much faster in the center than the outskirts, because it is more dense and it's radiating out a lot of X-ray energy. And that should mean that there should be something called a cooling flow coming from the outskirts into the core. Okay, so what are these cooling flows? So as the X-ray emit out the energy, then it forms this thing called the cooling flow. So as the stars are moving toward the center of the galaxy, or the BCG or the center of the galaxy, then we expect that to have a lot of new stars forming, or cold gas are going into the center of the galaxy cluster. And those are what we expect to see as a cooling flow. However, if you look at the actual galaxy cluster itself, you see that each one of these are the center cluster or the BCG, and you can see that none of them have this filament-like structure that are coming in from the outskirts to the core of the galaxy cluster, except the Phoenix cluster, I guess. Okay, so that means the idea that we have about the galaxy cluster are actually not exactly correct, because we don't see what we expected to see. Okay, we actually separated the galaxy cluster into two types, called the lilac cluster and disturbed cluster. For lilac cluster, for example, is ABL 1835. It's mostly cool core. That means the core of the galaxy cluster are much more dense compared to the outskirts, and it has some cooling, and it usually hosts radio loud galaxy or AGN. And it have this mostly spherical shape in the X-ray. Another type of galaxy cluster are the disturbed cluster or El Gordo. So El Gordo are mostly non-cool core cluster. So the core of the cluster itself is actually not as cool as the cool core. It doesn't have a lot of cooling. It usually have radio quiet AGN. And lastly, the morphology of the X-ray ICM are disturbed or asymmetric. And you can see that clearly in this picture. So you can see this bullet-like shape, which are what we usually is a cool signature for the disturbed morphology galaxy cluster. Okay, so these are basically the two types of galaxy that we know of: a lilac cluster and a disturbed cluster. Okay, so these are what we actually detect. So we found lilac cluster, we found disturbed cluster. We think we found maybe 50% lilac cluster, or another 50% disturbed cluster. However, these are not what we think galaxy cluster should be, because as I talked about in the previous slide, we talked about cooling flow and how is that happening inside the galaxy cluster, but we do not see any of that. Okay, so then the question is, what happened to the cooling flow? Why is there no star formation inside a galaxy cluster? So there are this thing called the suppression of star formation. So here is a histogram. The x-axis here, the efficiency of the cooling. So it's basically defined by the star formation rate divided by cooling rate. So here is a galaxy cluster, and as the X-ray energy are radiated out from the galaxy cluster, then the gas itself should be cool, and we call it m dot cool, because that amount of gas that are cooling as a function of per time. And then in the center, you would expect all these cool gas that are cooling out from the outskirts and then going into the center of the cluster. Then it actually forms new star, and we call that the star formation rate in a unit of solar mass per year, or how many new stars we actually forming per year. And then if we take the ratio between the two called star formation rate divided by the cooling rate, we see that we would expect that the ratio to be 1. So it should be equal between the star formation rate and the cooling rate. However, it's not 1. It actually peaked about 0.01 or only 1% of all the cool gas that are coming from the galaxy, from the hot gas in the ICM, actually cool and from the new star. So very few stars actually are formed from this mechanism. Okay, so and we call it the cooling flow problem because we don't see the cooling flow, and that is a problem. And then the answer, the quick answer to this problem is called the AGN feedback. Okay, so I'll show you a diagram of how the AGN feedback works. Okay, so here is a quick diagram of what the AGN feedback look like. So here is a hot gas, and then here are the BCG or the central galaxies. And then you can see there's a black hole and then the actual disk itself. And then as you can see, these hot gas are hot and it have a red color. So what happened is as if hot gas are radiate out energy, the main hot gas itself will cool down. And as it cool down, some of it will actually form a cooler cold gas. And this cold gas have its property as actually more dense and actually much more likely to form new star. However, as this cool gas are forming, it will, because it's much more dense, it will fall into the center. And as this fall into the center, then some of it gas will actually go into the black hole and actually activate the black hole called the AGN, or the active galactic nuclei or active galaxies. And that will actually activate the black hole and then create out this thing called jet or mechanical power, which actually remove out all the other cold gas and also heat up the actual hot gas, the main ICM to be a hotter temperature. And that means this hot gas could no longer cool down and form a cold gas. And that was preventing the cooling flow to actually happening inside a galaxy cluster. So as the black hole are turning back, as the black hole stop and then turn back into a passive galaxy, then the feedback cycle begin again. And that's why we don't see extreme cooling from this hot gas into the center of the galaxy cluster, and only few of them that we actually detected. Okay, so here is the example. Here is a quick diagram of what's happened. So basically, the gas radiate out X-ray energy, and that gas start to cool as it radiate out the X-ray. And then the agent got activated from all the cool gases are going into the center of the cluster. And then that agent activated create a large output of energy from the black hole, which heat up the gas. And as the gas cool down, then it becomes radiate out X-ray again. And it go into a feedback cycle called the AGN feedback. Okay, so here is a empirical evidence that what we see in the galaxy cluster. So here is the energy loss from cooling. So that is how much gas are radiating out from the galaxy cluster. So here is this part. And then mechanical energy in cavity, that is how much energy is agent actually putting into the system or into the hot gas itself. And that is and so is this part. And then you can see that these are the one-to-one ratio between the two. And you can see that there is a strong correlation between the energy loss from cooling and the mechanical energy in the cavity. And that means it is a good evidence that AGN feedback actually happening inside a galaxy cluster. Okay, so next is now that we know about AGN feedback and what's happening inside a galaxy cluster, to actually understand that we have to look for exception. And the most famous exception that we have in this type of galaxy cluster are the Phoenix cluster. And the reason that it's actually the most famous exception is because it has an extremely high star formation rate at 600 solar mass per year. So a typical galaxy cluster only have like a few solar mass per year star formation rate. And it have a really strong cool core, so the core is super dense in the center, and it have this relaxed morphology just like a typical cool core galaxy cluster. However, this extremely high star formation rate at 600 solar mass per year is implied that the AGN feedback actually not working or doesn't working properly in this specific galaxy cluster. Okay, So everyone will start asking the question, what happened to the Phoenix cluster? And to ask that question in another way is basically ask, how rare is the Phoenix cluster? So but that just means, how do you think we will be able to find this type of Phoenix-like cluster in our entire universe? Okay, and that leads me to the project and why I studied it. And the project called the CHIPS survey. And the CHIPS survey stands for the Cluster Hiding in Plain Sight survey. And just as the name suggests, we are looking for Phoenix-like cluster from a previously or sky survey, in this case, X-ray or sky survey. So before I talk about how is the CHIPS survey work, let me talk about how is the Phoenix cluster discovered in the first place. So the Phoenix cluster, if you look at it in ROSAT, which is an X-ray or sky telescope, you can see that it actually just look like a really dense point in the center, because the density of the center of the galaxy cluster is so dense that it actually just looks like a point source. So the ROSAT X-ray telescope always call this object a point source or not a galaxy cluster. Okay, so but however, with a bigger and better telescope like Chandra, you can actually see that the point source in the ROSAT images actually is just the really dense part of the galaxy cluster, and there are all these dense diffuse emission from the X-ray that you can detect that with the Chandra. And with even more Chandra data, you can, and once you remove the point source from the center, you can actually see so many more structure with the X-ray data itself. You can see these cavities that are detected from the edge from the galaxy cluster. Okay, so now the question is, how many of these what we call X-ray point sources are in fact a galaxy cluster? So that means other people have been misclassified these as X-ray point sources. However, some of them could just be a Phoenix-like cluster, like what we did with the Phoenix cluster. Okay, so here is my starting point. We did a ROSAT point source catalog, and that just lists every object that the X-ray telescope call a point source or just a point-like object. And each one of these dots are a one point source. And then the color just tells you the hardness of the point source itself. Okay, and to do that, the first step that I do when I get to MIT is matching the point source catalog with unknown or sky survey catalog, including WISE, 2MASS, and NVS, and some for the radio, just like what Mike talk about in the introduction. Okay, and then we pick the only brightest part of the matching. So here is all the match that we found, and then we only pick the top right corner, and that just because I mean, we could go further, but most of these probably just are collected, identified as a point source. So we only pick a really bright one. And that just means we have and that also, the reason for that is also it's much harder to follow up with a much bigger sample. And the next step for that is we actually do something called the optical follow-up. So we follow up each one of that ping point on the previous slide as an actual optical data itself. So on the top, we use the three telescopes called Sloan, Pan-STAR, and Pisco. I want to emphasize that all the green points here in the bottom are the new observation. So that's what I talk about when we talk about like 5-minute exposure per object. So each one of these green dots, we actually have to flew into Chile and actually observe this particular object one by one for 5 minutes at a time for each of these in the southern sky. And the reason for that is because the northern sky have many more telescopes in the past, so it have a lot more available public data. So Sloan and Pan-STAR cover almost all the sky in the north. However, in the past, there are not that many telescopes in the southern hemisphere, and then it just started getting to have more now. But back then, we don't have a lot of telescopes in the south. That's why we need to use our own individual observation for each one. So here are a quick property about the telescope itself. So Sloan and Pan-STAR are all sky survey. Sloan is 2.5 meter telescope in New Mexico, and Pan-STAR is 1.8 meter telescope in Hawaii. And the purpose of these two telescopes are not for looking for new galaxy cluster, but we just use the data itself to find a galaxy cluster. And then Pisco is a new instrument called the parallel imager for southern cosmological observation. And it's a new instrument that put on the 6.5 meter Magellan telescope in Chile. And the reason it's new is because they actually take 4 band images at the same time. So G, R, I, and C band. So that means with only 5-minute exposure time, I get 4 images of 5-minute exposure each. And then you can actually study each one of these point sources very fast. Instead of taking 20 minutes per object, then it's down to 5 minutes per object. Okay, so here are examples of what optical images look like in the different telescopes. Sloan, Pan-STAR, and Pisco. So basically, we make the Pisco images with a much bigger telescope, but only with like 5-minute exposure, so that the depth of the Pisco is about the same as Pan-STAR and Sloan. So we get roughly the same depth in all 3 telescopes. Okay, so here is the main result. And before I talk about that, let me show you what it means first. Okay, so the x-axis here is redshift. So that is how far away the source is from us. So low number is closer to us and higher number is further away from us. And richness is basically the number of galaxies that I counted within a field of view. And that just means 10 galaxies and then 20 galaxies. And this blue line are cut that we used. So, and the cut we estimated from this for this thing called the flux limited line. So these are known galaxy cluster from the ROSAT catalog. And then, as you can see, because the X-ray are strongly dependent on the density and its brightness, then farther away galaxy cluster, we only find a really bright one. And then we have this flux limited line. We actually fit this flux limit line with the richness expected from each of these galaxies, and then we get this slope. And then from that slope, we can convert this line into a richness redshift line. And these are the cuts that we actually use to cut, and then we select every galaxy or every object above the blue line. Okay, and then we did something called collected richness, because as we go further away in a distance, it will be much more difficult to find fainter galaxies, because fainter galaxies are much harder to find at high redshift. So we have to do some correction. So we collect for the number of galaxies that we would expect to find in each location. And there are some correction that we provide. Okay, so here is the main result. The orange point here are known galaxies, so like a Phoenix cluster, and all these well-known galaxies like CHIPS1356 or ALAS 09104. So these are known galaxies that other people have found in the past. However, these 3 points here are new galaxy cluster that nobody have found before until the CHIPS survey. And then there are 2 false positive that we have detected. And what we did is we confirm all these blue points here with the X-ray telescope with Chandra, so that we actually confirm that we see both the point-like feature and also the extended emission. Okay, so here is one of the main results from the CHIPS survey. That means we try to answer how rare is the Phoenix cluster or the occurrence rate of the Phoenix-like cluster. Combined with all the X-ray cluster sample like Reflect, EBCS, and MAX survey, we found that there are about 460 galaxy clusters found with the previous survey data. And the number of objects that we call Phoenix-like, or every object that are above the blue line, is roughly 10 galaxy clusters. And that means the occurrence rate is about 2 plus or minus 1%. Okay, so now to answer the question, how rare is the Phoenix cluster? The answer is it's pretty rare, as 2 plus or minus 1%. Okay, so what does 2% mean? So the 2% could mean that 2% of the galaxy cluster have this feature all the time, or it could mean that all the galaxy cluster only have this feature 2% of the time. So what we think happen is each one of these galaxy cluster have this like cool Phoenix-like cluster, or like this extreme rapidly cooling phase as about 2% of the time. So as a ICM temperature, and when it happens to be extremely cool, it will come down. But since we only observe at one epoch of observation, we only find 2% of the sample have to have this feature. So that's what we think happening in this survey. Okay, so that's just 2% of the time. Okay, so here is the implication. one of the possible theory for AGN feedback called chaotic co-accretion. So that what happening inside the AGN feedback is called instability and condensation. So as the hot gas are started cooling, then some part of the cloud or the gas itself become unstable and it start to condense, and those condensed gas start to falling down and then activate the AGN. But what we think happening is there is a delay between where the AGN become active or as the gas are falling into the BCG itself, and the actual activity that AGN can have an impact on the actual galaxy cluster as a whole. And this delay between where the AGNs start to become activated and where it actually have an impact on the whole galaxy cluster, we think that could roughly equal to the 2% or the 2% lifetime of the entire galaxy cluster. And in this simulation that it was done by PRASAD 2020, he can see that there are more cooling only a really short period of time. And in a typical phase, there will be not much cooling except at so that's why it called chaotic, because it only happens sometime when the instability causes the falling and activate the AGN. Okay, so go back to this is also the first galaxy cluster I want to introduce is CHIPS1356 or chip 1 that I usually normally call. So here is our first chip cluster that we have found surrounding PKS 1353. So here is a picture of a galaxy cluster in optical and X-ray with Chandra. And Chandra is a big telescope that we use to confirm the galaxy cluster. You can see that clearly really bright point source in the center and a really faint emission in the X-ray that you can see go in the outskirts. And those are a really strong signature for galaxy cluster. We estimate the mass of a galaxy cluster to be about 6.4 times 10 to the 14 solar mass. It's one of the 5 known galaxy clusters that have a radiative power or the energy that coming out from the AGN in terms of radiation equal to the mechanical power or the jet power. And this one is a really strong evidence that we actually found a galaxy cluster that have been misidentified by other previously identified X-ray survey. Okay, so now I want to talk about my favorite cluster. Well, so another cluster that we found called CHIPS1311. Okay, so here let's go back to this one. Okay, so here is CHIPS1311. So it's at a higher redshift. It have a higher richness, or expected a higher richness, and it's also okay. So here is CHIPS1311. We call it Phoenix with algorithm, and the reason for that is Phoenix cluster is, as I talked to you earlier, is the most famous exception. So it have extremely high star formation rate. It have a strong cool core, and it also have a relaxed morphology in ICM. However, Algodo is the most massive galaxy cluster that we know of. It have a really low star formation rate in a non-cool core cluster, and it have a highly disturbed morphology in ICM. However, CHIPS1311 plus 4455 is a new galaxy cluster that we have found with the CHIP survey that have a really extremely high star formation rate with a strong cool core in the center. However, its morphology is actually not relaxed like a Phoenix cluster, but it's highly disturbed morphology, just like Algodo. And why is that important? Okay, before I talk about that, let me show you what it looks like. So here is an image of a CHIPS1311. So the central here is the BCG, and you can see that it have a color similar to the Phoenix cluster in the center. So it have white or blue, like bluish shade. And it have all these red dots here, member galaxy. So each one of these are individual member galaxy as a part of a giant galaxy cluster. And here is a scale for reference. And these are just forecast star. Okay, so but these are not what massive galaxy cluster should look like, because most extremely high star formation system like a Phoenix cluster that we know of are always in the relaxed morphologies or in the normal Okay, so here is our image in X-ray. So we observed this guy also with Chandra data. It's observed in 2019 with ASIS-I for 30 kiloseconds. This image have been adaptively smooth to see the feature in both in the center and in the outskirts, and it's show a cool core in the center. So here is the densest part of the galaxy cluster, and it have a similar property as a typical cool core. However, on the large scale, you can see that it's no longer spherical or circular shape on the large scale, but it instead in this highly asymmetric shape. And that is a strong signature for disturbed galaxy cluster. Okay, so come back to this image again. So here is the galaxy cluster, and then what we did is we actually get a much better angular resolution images on the optical, because these are just images that we took from the ground. However, to actually study the property of the BCG in more detail, we need a better images from space. And this is what we found with Hubble. Okay, so now is the images that we detected with Hubble. What happened is the central galaxy cluster, the central galaxy in the side cluster is no longer like a white or blue light color now. The actual galaxy cluster itself have a really normal looking elliptical color, like a red or red yellow color. However, you can see that there is this very nice filamentary structure that are compact in nature, that are only coming in and out of the galaxy cluster itself. So we think this could be the cooling flow that we would expect to find in any other cluster, but we have not seen. And these are a strong signature that these galaxy cluster are actually undergo a cooling flow, just like what we've seen in the Phoenix cluster. And then that's why these clusters are called Phoenix-like in nature. Okay, if we zoom out a little bit, and then let me tell you a little bit about the Hubble images that we observed. The Hubble image also observed in 2019 during a mid-cycle proposal, because we think it's an interesting cluster to study. It have two orbits, so it have two orbit of exposure. So one orbit is a shorter wave band for blue continuum and the bright O2 doublet, so that we can actually only focus on the star formation part of the galaxy cluster. And then on another orbit, we use a really wide red band continuum to get the red continuum from the elliptical galaxy. So these all these are coming just from one band images. Okay, so if we put the X-ray on top of your optical image, you can see that the center peak of the X-ray, or what I call a cool core, is actually co-located at where the BCG is, and also where the filament and trace structure actually happening inside a galaxy cluster. Okay, let me put in a much more easier to understand images. Okay, so here is a contour from the X-ray image that I showed you in the previous slides. And then when I put that on top of the optical image, you can see that the peak of the X-ray actually co-located with the BCG and also at the filamentary structure of the galaxy cluster itself. So that means that where it's densest in the X-ray, where it's cooling the most, that's where we see the cold gas actually forming in the optical image. And if you look really carefully on the northern part of the image, you can also see some filamentary structure going in the northern direction. And that is also co-located with this smaller peak that we found in the X-ray. And those two could also have some connection, but we would need a much higher resolution images to actually study what's happening inside this galaxy cluster. Okay, if we put everything in context of the same luminosity and redshift image, you can see that here is the same flux limit of all the known galaxy cluster that we have been detected with the ROSAT X-ray telescope. And our two new galaxy cluster is CHIPS1356 and CHIPS1911. It way above the flux limited line. The third one, we just only found the upper limit, so it's probably not the massive galaxy cluster, but these two are. And that means all these known X-ray survey that have been observed in the past have been missed these two galaxy clusters for the past 20 years. And with the CHIPS, and only with the CHIPS survey that we have rediscovered these two for the first time. Okay, so that's it for CHIPS, and let me give you a quick conclusion on what the chip survey is, and then we can go on to the second part of the talk. Okay, so basically the rarity of these extreme cases tell us that the co-chaotic accretion or the CCA could be a mechanism for the feedback. We also found this new galaxy cluster called CHIPS1356 as a typical storm cool code, but with a very bright central quasar. And lastly, we found a new mode of cooling in CHIP 1911, which is a massive starburst inside emerging galaxy cluster. And okay, so now I will shift gear, not a little bit, but a lot, and move to the second part of the thesis, which is the evolution of AGN activity in the brightest cluster galaxy. So now I no longer talk about chips. And to emphasize that, I changed color of the background just to emphasize that it's no longer about chips. And it's the project called the evolution of AGN activity in the brightest cluster galaxy. And internally, we call the SOSA project, and just because we need SOSA with the chips. Okay, so to understand, so the main goal of the project is try to understand the evolution of the AGN feedback. So what happened? Okay, so we know AGN feedback happened right now in the present, but we don't actually really sure what is happening in the past, or is AGN feedback fully activated all the way in the past, or at the higher chip object, or is it just becoming fully activated or fully exhibited only recently? And is there an evolution of how the AGN feedback work over time? And that's what we try to understand with this project. Okay, and to do that, we using this thing called the fraction of AGN-hosting BCG, and that just means the fraction of a BCG or a galaxy that hosts the AGN in the center. And here is a very simple example. Here is a highlight chip or every galaxy cluster that are much further away from us. And here is a lower chip galaxy that are much closer to us. And then we just start counting the number of BCG that have an AGN in the center. For example, in this case, we count that there are 5 out of the 6 galaxy clusters that have the AGN hosting in the center, and that means the fraction is 80%. And then in this image, you can only see the fraction of about 2 out of the 6, so that means 30%. So that means there is an evolution of the fraction of AGN hosting BCG that are changing from the past to the present. And that is what we will do in this project. Okay, so, and here is a quick outline of what I will talk about in this part of the talk. So the first thing I talk about the BCG selection. So we have to actually identify the BCG first, because we only care about the central galaxy and not this member galaxy, whether they have AGN or not. And then we have to identify which one of these BCG have AGN or become active in the in this black hole. And then I'll show you the result and the implication. Okay, so here is the BCG selection. So first thing first, we start from the SPTSC cluster catalog. So that are more uniformly selected in Redshift. So you can see higher distant galaxy cluster and low Redshift galaxy cluster. And then we basically estimated the BCG probability by using the Redshift and stellar mass probability distribution. And then we randomly sample to find the most massive galaxy at the Redshift of the cluster as a BCG. To say it in other words, we basically modeling each one of these galaxies, and then we basically use the probability distribution of it to be Redshift at the Redshift of the galaxy cluster, and also the most massive galaxy in that field view. And then we call it a BCG. So for example, in this case, this galaxy is take about 90% of the time to be a BCG, and this galaxy is about 70% of the time to be a BCG. And then this probability are what we use to actually identify the BCG selection. And then we calculate the probability for each one. Okay, and then the second thing is, now that we have the actual BCG selection, so we know which one of these galaxies in each galaxy cluster are the BCG, then we have to identify which one of these are the AGN. And to do that, we first have to look at the SED of the galaxy and the AGN first. So here is the SED, the red, the black solid line here are the total emission from the passive galaxy. And as you can see, if you have an AGN-like galaxy, not passive, then emission will be get boosted in basically in all wavelength. So in mid-infrared, in optical, in soft X-ray, and hard X-ray. So that means if you want to only study an obscure agent, you can use any wavelength to study like mid-infrared optical. However, there are this type, another type of agent called type 2 agent or obscure, and that just means that there is something that are blocking the light from the agent itself. So it could be dusty torus or and that show here, for example, in a passive galaxy, you can see that the obscuration from the dusty torus actually basically reduce the optical light and the soft X-ray light to become almost non-existent. And then so you only see the emission in the mid-infrared in the passive galaxy, and the same thing happening in also in the AGN. So that means if you want to detect both the AGN in type 1 and type 2, you cannot use optical or X-ray into a soft X-ray to find the galaxy to find the AGN. So that's why we use mid-infrared color to actually use to detect the AGN, because the mid-infrared color, the mid-infrared light is got boosted in both an obscure and obscure agent compared to the passive galaxy. Okay, so here is what we did with the AGN selection. So here is the color. So W1 minus W2 is a color. So up a higher number is redder in color and lower number is bluer in color. And here is a redshift. That's again, zero redshift is closer to us and higher redshift are further away from us. And then the orange solid line here are the expected color for passive galaxy. So these are basically what color would we expected to see in a typical galaxy that are not active or not AGN. And then everything that are redder than that in color, it should be AGN. So that's why we draw this green dash line here as a cut. And everything above this line is, we call them a galaxy AGN. However, other work that have been done in the past usually only use a constant cut that only apply in some certain cut. And the reason for that just because of this kind of work doesn't actually know the redshift of an object itself. So doing more conservative cut would be better to select AGN. Okay, so now that I subtract all the data point here with the orange line, then we get this thing called a residue. And basically, we call everything above the green dash line here as a AGN select candidate. And we separate the data into 4 different bins such that each bin have the same number of BCG so that they have a similar statistic. Okay, and here is the main result. Basically, we see that the fraction of AGN-hosting BCG increasing with redshift. So we found is almost 0 AGN found in the first redshift bin, and there are about 10 to 15% of the BCG found in the higher redshift bin and the AGN. And however, these are, I mean, it looked like a really big increase. However, we actually cut the y-axis only at 20%. So 100% basically means every BCG at the AGN is not in this plot. So even though there are more number of AGN at high redshift, the most majority of the BCG at high redshift are still passive galaxies. Okay, we also compare this work with a lot of other works. First, we compare it with X-ray bicluster. So that is just a sample that Julie worked in 2013 that only compare with a really bright X-ray bicluster and look at the cavity power to find the AGN. And then you can see that she sees some increase in redshift. And when we scale the data down to a reasonable sample that we use in X-ray, then we can see that the results are matching pretty well. We also compare our work with the field galaxy. So field galaxy in this case just means every galaxy that are not part of a galaxy cluster, and we start counting how many of them are AGN and how many of them are non-AGN. And you can see that there is also an increase in redshift in both in almost all the work that we found, and it also consistent with what we found with this work. And lastly, we also compare this work with starburst hosting BCG. So no longer compare with AGN, but galaxy cluster that have a really bright or high star formation rate in the center of the BCG. And you can see that when we select a cut such that it is an extremely high starburst galaxies, then the trend of increasing in redshift are the same between our work and also my work in 2016. Okay, so what does that mean? What is that telling us about the AGN feedback and its evolution? So one way to explain this finding is that there is abundance of cold gas as high redshift. And why is that important is because most of the BCG or the massive galaxy in the center, they're basically the most massive galaxy. Then it has to grow by merger. And because of all these cold gas are available in smaller galaxy or member galaxy, as these smaller galaxies are falling into the BCG and form a much bigger BCG, then all these cold gas are enough to actually become a fuel for AGN accretion, which then increase the likelihood that we will find AGN bright BCG in the center of high redshift galaxy cluster. In this image, basically what happened is because of the cold gas, when the galaxy has when the member galaxy with a large amount of cold gas are colliding with the BCG, it provides enough fuel such that it activates the BCG. However, at low redshift, then we call this dry merger. So it doesn't have a lot of cold gas when it's merging, it doesn't actually give you any new fuel to fuel the AGN. So it doesn't activate any AGN accretion. So this is one of the implications that we think we found with this work with this evolution. Okay, I'm almost done. So basically, what now? So I'm just gonna give you one slide of what I hope to study in the future. So first thing first, I want to definitely work on CHIPS1311 more. In fact, we actually proposed for more Chandra observation with CHIPS1311 in this past cycle. And we're hoping to, so now we only have 30 kiloseconds of data. We're now asking for like 200 kiloseconds of data to actually get a much more higher angular resolution in the center to actually see what is happening inside a galaxy cluster and how is the central part of the galaxy cluster matching with the disturbed morphology from the outskirts of the galaxy cluster. And then, okay, and then we also want to expand our chip. So if you remember in the very first slide about the chip survey, we actually combine with the X-ray data with the mid-infrared color radio data, and also and then we only cut those objects that are bright in every wavelength. However, we actually found that a lot of galaxy cluster doesn't have to be radio bright. So some galaxy cluster have a really bright AGN, except it doesn't have a radio bright or even infrared bright. So we basically remove all those constraints to cover a larger sample of sample and go back and look at individual point sources that we found from the ROSAT from the beginning. And we just call that caso. And then actually we think we might find a new galaxy cluster with a really bright point source that could be AGN. Actually, we know it's a bright quasar in the center, and this could be a really bright, a really massive galaxy cluster in the background, surrounding this really bright quasar in the center. However, they are super preliminary because I'm just working on that for the past 2 months, and we still need a lot more data to confirm whether we actually see a new galaxy cluster. Okay, my last slide. Basically, here is what I did for the past 6 years that I did working with Mike here. The main result that we found is the rapidly cooling galaxy clusters, such as the Phoenix cluster, are pretty rare, and we found it as 2%. We found that the cooling flow can survive merger, so this cooling flow can actually exist even in this merging or disturbed galaxy cluster. And lastly, we found that there are more AGN accretion happening in the past compared to what we see in the present. So we would expect to find AGN by galaxy cluster in the past. Okay, and my last slide and my last sentence that I want to leave is finding more extreme galaxy cluster, such as any of these objects, will actually help us unlock the mystery of AGN feedback. And that's it for my talk. And yeah, I think, okay, so next, next I will have a really quick acknowledgement of all the people that involved. Okay, so first I need to thank, all the committee that are here today. So I have to thank Mike Mark and Call as a really good community that we have been talking for the past 3 years, and then especially mine because I started working in Galaxy cluster without actually want to work in the Galaxy cluster in the first place. I came here to do exoplanet, but I found Galaxy cluster work better, so now I'm doing Galaxy cluster. So I'm really thankful for my tutor, for Sada. She actually accept me, and then because I don't have any background in Galaxy cluster or X-ray observation. Actually, I don't know anything about the work until I joined MIT. So it was a really fun 6 years, and then I learned a lot because I start from zero. And then and from the group, I also have to thank Matt Bellis and Alison and the first 2 postdocs that joined our group. And because our group are really small at the beginning, and then those 2 actually make it more like a group and not just 2 of us talking every day. And they also help a lot with the observation of the CHIPS1356 and Arson also did a lot of the ROSAT work. And then I have to thank Michael and Florian for another 2 members of the group. Michael helped me a lot actually because he knows a lot more X-ray when he started than what I did. And then Florian also helped a lot when he's here. And then the last 2 are Mark Borwin from University of Kansas and Eric Miller from MIT. Those 2 are basically my other 2 recommendation letter writer, and I applied to like almost 50 places. So I'm super thankful that they actually finished writing all my letter application. And then and there are so many more people that I have to thank that I met during MIT time. So I could not just gonna name them all, and I just gonna show you a lot of pictures. So these are the only pictures that we have of all the 6 of us before they all left. So the 2 postdocs that we have now become a professor. And then we used to have, so we usually do defense in solarium right here, and then we usually just waiting and eating the cake outside. And these are basically all the people that we have back then. We don't actually have a really small group of grad students, and now we have way more, like a lot more. And then we also, and here is we also did some fun thing while we also studying. And now we have like too many, so now we cannot fit in the film anymore. And then as we all know, COVID happened, so now we have to move everything in Zoom. And now we also do some fun thing with a mask. And we also give some presentation at the conferences, and then we also have a physics cohort in my year, which are not really big. And of course, there are a lot more Thai people that I can think of in Boston area. So that's why I have to thankful for them to actually give me something else to do that's not astronomy. And also my friend from college, which actually also at MIT and other places in Boston area. And of course, it's my family because I came here for the past 10 years in the US, and I really miss them, but now that I'm finished. Finally, I can get to see them again. And that's it. Thank you everyone for coming. And if you have any question, I'll go back to the last slide. Okay, thank you.
So